Good morning, everybody, and welcome to a special Bow Tie Thursday edition of Algebra 2 with me, Mr. Poley. It's a special edition because if you notice, I not only have a bow tie on today, but I also have suspenders. Suspenders, in my opinion, do a great job tying the whole outfit together. But, that's just my opinion. Everybody's entitled to their own. Either way, we're going to get started today with systems of linear equations. We are on page 101, and then we will be flipping that page to page 102. Okay, systems of linear equations falls right within our linear functions, equations, and their algebra unit. Okay, so this is all based on linear functions. And you guys know that because you've been with me for the past few lessons where we've been very deeply studying linear functions. So today, again, linear systems of linear equations. As you'll see on the board here, we are starting with a 2x2 system, which means there are two equations and two variables that we need to solve for. We will be then moving on to 3x3 systems, which if you can guess based on what a 2x2 is, a 3x3 system is three equations with three unknowns. So not only do we have an x and a y that we need to solve for, but we also have, you guessed it, a z, that last letter of the alphabet. So we will be solving for x, y, and z, as you can see right down here. Okay? The idea of solving a system is that we find the values of these variables that make each equation in the system true at the same time, simultaneously. Okay, so when we solve this, x and y, we will have one value for x and one value for y that will make this equation true and this equation true at the same time. How cool is that? Linear systems are things that show up in mathematics all the time, especially when you get to higher levels. And remember, that's really what Algebra 2 is setting us up for, to be able to conquer those higher levels of math. So linear systems and how we solve them is very important to mathematics. So we're going to take a look at these today. And you guys have had some experience with solving linear systems before, whether you know it or not. Okay, when I've asked you a couple times to find the point of intersection, you're finding the point of intersection of two equations, two lines, two functions. Okay, and that is solving a system. Because you find the x and you find the y, you find that point that satisfies both equations. So that's solving a system. You've already done that before. We've done that before. So we're just taking our skills and our knowledge to that next level, just getting up a little higher, okay? And 3x3 systems, I know I say this maybe a little too much, but I think these are a lot of fun, okay? It is procedural, so it is a process that we have to follow to solve each system. And because of that, that's what makes it slightly challenging, okay? It's a somewhat lengthy procedure, which doesn't mean we can't get through it, because we certainly can. But it just takes a little more time and a little more energy to make sure you're doing things correctly. Especially, again, like I always say, with the signs. So positives and negatives play a huge role in solving linear systems. So you really have to watch your steps. Okay, I don't want to see anybody trip. But if you trip, make sure you get back up, and that's okay. All right, so let's start it out here with exercise 1. It says solve the following system of equations by substitution over here, elimination over here. Okay, if you notice, both of these systems are the same. So we're just using two different methods to see how they both result in the same solutions. All right, so to solve with substitution, one thing we need to remember is that one of those equations has to be either in x equals form or y equals, because then we will take whatever that variable equals and substitute it into the other equation, hence substitution. So I'm going to focus on my one equation now, where one of my variables has a coefficient of 1. That's the second equation here, because that coefficient on y is only 1. So I'm going to subtract 2x from both sides to get that in y equals form. Y equals negative 2x minus 7. Okay? Now I can take this expression here, which I know is equal to y, and I'm going to substitute this in for y in my other equation. So I'm rewriting that first equation, 3x plus 2y, but instead of putting the y there, I'm substituting in what I know y is equal to from my other equation. All right, now I want to distribute this too, combine my like terms. 3x minus 4x minus 14 equals -9. Okay, so I want my x's on the left and my numbers, my constant on the right. So I'm going to add 14 to both sides and combine these here. So I get -x equals +5, because -9 plus 14 is 5. So if -x equals 5, that means x equals -5. Okay, and you can find that by multiplying by -1 or dividing by -1. Okay, so we have x equals -5. Although it might seem like we're done because we have a solution, we are not yet finished. We will take this value for x and substitute it into either of our original equations. Either one doesn't matter. Whichever one we choose doesn't matter, because remember, the x that we find and the y that we find will satisfy both equations at the same time. So we can use either equation to find our value of y. Since I already have y alone here, I'm going to substitute in -5 for x, and we'll get my value of y. I'm going to do that right up here because I have a little more room. So I'm rewriting that, but again, instead of that x, I'm substituting in my -5. So I get y equals 10 minus 7, which means y equals 3. All right, so I would put my x value in a box here and my y value in a box here. Okay, normally I would say to write this as an ordered pair. If my smartboard will let me. -5, 3. Okay, my x and my y. But if you just had the values like this, that would be okay for this. Because we're not, even though we are finding a point of intersection, it's not really important right now, right? We're just getting used to solving this system. So those are my two values for x and y. All right, -5 and 3. Now we're going to solve this system, hopefully get those same answers, but we're going to do this by elimination, because we will be using a lot of elimination when we get to the 3x3s. Okay? And elimination works like this. You may or may not be familiar with it. Okay? As we have these equations right now, we cannot eliminate anything. We need to manipulate one of these equations so that the coefficients on a single variable will be opposites. And you'll see what I mean in a second. Okay? I see my x variable, or my x coefficient is 3 here and 2 here. My y coefficient is 2 here and 1 here. So I need to think, what can I multiply one of these equations by so that either the x coefficients will be opposites or the y coefficients will be opposites? Okay? And there's more than one right answer, but we want to try to find the easiest way to go. So I'm going to take my second equation here. I'm just going to label these. That's equation 1, that's equation 2. Okay, I'm going to take my second equation and multiply it by -2. So watch what happens when I multiply it by -2. Put -2 out front of the whole equation. Okay, because the only reason we can do this multiplication here is due to the multiplicative property of equality. Okay, if we multiply this number by every term in that equation, that is a legal move because it doesn't actually change anything. Okay, it does not change the equation. Like I said, we're just manipulating it to our advantage. Okay, it's totally legal in mathematics as long as you multiply each term by that number. So by doing that, I get negative 4x minus 2y equals 14. Okay, now I'm going to take my first equation and just rewrite it under this equation, under this new equation. And what's happening here? Hopefully you guys can see that my y's now have opposite coefficients. One is a negative 2, one is a positive 2. So with that, we can now use the addition property of equality. Okay, we can add these two equations together. So negative 4x plus 3x is negative x. Negative 2y plus 2y is 0. Okay, we just like that, we eliminated y. That was the whole point in this process here, to eliminate a variable. So now we have negative x equals 5, because 14 minus 9 is 5. And if you notice, that matches exactly what we had over there. So that means x equals negative 5. All right? So that's our x value. And we would again then take that value of x, substitute it into x in one of these equations, and get our y value. I'm not going to do that right now since I just did that over here, and we know we're going to get the same solution. Okay, but the big reason for showing this example here was to start to get used to this idea of elimination. Because again, that is what we will be using a lot to solve these 3x3 systems. Okay, so let's move on here. All righty. Consider the 3x3 system. Who's ready for this? Yeah, let's see some excitement. Let's see some enthusiasm. 3x3 system of linear equations. As I mentioned, each of these equations now has an x, y, and a z. Don't get scared by that z though, okay? He's not that scary. All right? When we are done solving this system, we will have an x value, a y value, and a z value that solves each of these, or satisfies each of these equations at the same time. It's really cool how that can work out. And you can picture that then maybe as a three-dimensional plane instead of just an x and a y axis. Now we have a z axis coming out. Okay, so there's those three values where these three different equations in 3 dimensions all meet at a single x, y, z point. But I'm getting a little ahead of myself now, so let's draw back here and just work on solving this equation. Let's find those values. Okay, let's see. Each equation is numbered in this exercise to help keep track of our manipulations. All right, just like I numbered up above. The addition property of equality allows us to add 2 equations together to produce a third valid equation. Right, that was what I showed in the second method above. Create a system by adding equations 1 and 2 and 1 and 3. And then they asked, why is this an effective strategy in this case? So let's see what happens here. You're going to take equation 1, which is 2x plus y plus z equals 15. And I'm adding that to equation 2, which is 6x minus 3y minus z equals 35. Okay? Hopefully you guys noticed just from me writing those down or from you looking at the equations that our z variables now have opposite coefficients here. We have a positive z and a negative z. So when we add these 2 equations together, we get 8x minus 2y plus 0, because these variables eliminate each other. That's the whole point here. And that equals 50. Okay, we added 2 equations together to get a third valid equation. Okay, we added equations 1 and 2. Now we're going to add equations 1 and 3. Okay, same idea here. So I'm rewriting equation 1. 2x plus y plus z equals 15. And I'm going to add this, like they told us here, to equation 3. So I'm rewriting equation 3, negative 4x plus 4y minus z equals negative 14. Alrighty. Again, they told us to add these two because you'll notice our z variables have those opposite coefficients. And that's exactly what we need to eliminate. So add these together, we get negative 2x plus 5y plus 0. Again, those eliminate each other. And that is equal to 1. Okay? So you'll notice both of our new equations only have an x and a y. Now we're really working with a 2x2 system like we did in that first exercise. Okay, we add two sets of two equations together to eliminate the same variable. We eliminate z in both of these to get these two new equations that only have an x and a y. Because now we can solve this 2x2 and then fill in backwards to solve the 3x3. So use this new 2x2 system to solve the 3x3. All right, so I'm going to rewrite both of these. 8x minus 2y equals 50. Negative 2x plus 5y equals 1. So now, just like I showed above when we were eliminating, we need to examine these equations, look at them closely. What can we multiply one of these equations by so that the coefficients of either the x or the y will be opposites of each other? We have an 8x and a negative 2x. We have a negative 2y and a positive 5y. Okay, well, hopefully we're focusing on the x's here because both x coefficients are even. That means it will be a little bit easier to get them to be opposites of each other. Okay, we can just multiply this second equation by 4, which gives us negative 8x plus 20y equals 4. Now I'll rewrite the first one underneath. 8x minus 2y equals 50. And looky there, negative 8x plus 8x. Okay, when we add those together, the x terms eliminate each other. That's exactly what we wanted, because now that just leaves us here with 18y equals 54. And that's a one-step equation that we all know we can solve by dividing by 18, divide both sides by 18 to get y equals 3. Okay, y equals 3, that's the first step to this 3x3 puzzle. Y equals 3. Okay, so now we take that y equals 3 and go back to either one of these equations here with just the x and the y, and we substitute in for y. So I'm going to use this one here just because it's closer to me right now. Okay, so negative 2x plus 5 parentheses 3, because I know that y value equals 1. Get negative 2x plus 15 equals 1. Subtract over 15, I get negative 2x equals negative 14. And then dividing by negative 2 gives me x equals 7. X equals 7. So far I know that y equals 3. X equals 7. I'm missing one variable. Now I need that z. Okay? So I can use either one of my 3 original equations. And I'm going to work with that first one, because it looks easier to me. It looks a little simpler. So I'm going to rewrite it, but to fill in, to substitute my x and y values. So I have 2 times 7, because that's my x, plus 3, which is my y, plus z, which I don't yet know, but I will very soon. 14 plus 3 plus z equals 15. So 14 and 3 together is 17. So I'm going to subtract 17 from both sides. And I get z equals negative 2. And just like that, guys, we just solved a 3x3 system. Your first one. Give yourselves a round of applause. And there's more where that came from. Okay, we got our x equals 7, y equals 3, z equals -2. Okay, and again, these three values satisfy equation number 1, equation number 2, and equation number 3, okay, at the same time. I'm not going to go through the checking process, but if you guys want to, if you want to trust me a little more, if you maybe don't believe that that can possibly be true for all three of those, go ahead and substitute those into each equation, and you'll see that they do all equal out. Okay? So guys, the process we just went through is how we solve each 3x3 system. Okay, we start with two sets of two equations. So remember, here we did equation 1 and 2 and equation 1 and 3. Okay, we use those equations to eliminate the same variable. So we get two different equations that have two variables only. This one has an x and y. This one has an x and y. Okay, you then use those two new equations to eliminate that other variable, or the second variable, which here we eliminate x's, and that allowed us to solve for y. Okay, and once you solve for that first variable, you just start to work backwards. Okay, we used one of our new equations, substituted in for y, to get our x value. Then we went all the way back to the beginning and used one of these three equations, substituted in for x and y, to get that z value. Okay, and once we have all three of those values, we're done. We solved it. That was a good job. Okay, again, guys, this is a tedious process. It is rather lengthy. Okay, it follows a nice procedure, though, so you just really have to be careful of your steps. Make sure you're doing things that make sense. Make sure your positives and negatives make sense the way they work out. Okay, and if you need to, take that time to check yourself at the end. There's no shame in that, none at all. All right, let's see. I'm going to pause here and resume shortly.